It's May. Just it's May. That's like the last month of school. May. We've made it. It took a weird route this year. We got there. We were sitting in class in March. Suddenly, we're home all the time, and now it's May. That's all right. We like May. Since it's May, we don't have a whole lot of school left this year. But we do want to cover some parts of our next unit before we run out of time this year. And we're going to get into circles today. And there's some really cool stuff to learn about circles. So strap your seatbelt in. Don't fall out of your comfy chair there. And let's take a look at what we're studying today. All right, here we go. Let's take a look at what we have. All right. Lines, angles, and curves. We're going to be looking about different things about circles today. So the defining moment. These images show some line segments that are chords and some that are not chords. So this is going to tell us the difference between a chord and something that's not a chord. Chord, spelled C-H-O-R-D, chord. So these are chords. Okay? These are not chords. Notice the difference? Notice the difference? It wants us to write a definition of a chord. A chord is a line segment. All right, those are all straight. Beginning and ending on a circle. So we're going to say line segment beginning and ending on a circle, right? Because it starts and ends on the circle. These do not. So this one goes from the center to the circle, but that is not a chord. A chord would have to go from the circle to the circle, not from the center. That's a radius, right? That's a radius. We know that. So chords would look like that. All right, so let's move on. Review that if you need to. Arcs. Let's look at an arc. So this shows some shapes that are arcs and some that are not arcs. Arc. Not an arc. Not an arc. Right? So arcs are part of a circle. They have a beginning. So a definition of an arc, it is like part of the perimeter of a circle. Just the part, outside. We're not taking a chunk of the circle. It's not like a piece of pie. We're not taking all of that. Just part of the outside, the perimeter. So this is not a circle. That's why we don't call that an arc. It does run along there, but this is a chord, right? We just learned that on the last page. A chord goes from one point in the circle to another point in the circle, straight line. But these follow the circle. Part of a circle would be an arc. All right, let's get rid of that one. Let's go to another one. All right, central angles. So we've got a lot of vocabulary we're doing here. Central angles. Central angles, we know what an angle is, but for a circle, we have something called central angles. And central angles work like this. Central angle, and these angles are marked right there. That's the central angle. These are not central angles. See, there's the angle marked down there. Here's one over here. This one over here. Central angles, center. Hey, they all go from the center to the edge of the circle. So central angles are made up of two different radii, right? A radius and another radius to make a central angle. So a central angle has to have the vertex in the center of the circle. The turning point of the angle, the vertex, has to be the center to be a central angle. Otherwise, it's not. An angle from center to circle with vertex at center. All right, we could probably phrase that better, but that kind of gets the point across. It's an angle that starts from the center, goes out to the edge of the circle, touches the circle on both ends, and it would be a vertex at the center. All right, we've covered those. Let's look a little bit how we get the measurement of these things. The measurement of an arc. All right, so we know how to define how many degrees an angle is. We can measure that. We have our protractors that we can do that. We can figure out how big that is. So how big is this? Arcs use the same measurement as the central angle. So since this is 60 degrees, this is a 60-degree arc. That's a 60-degree arc. So DC or CD, whichever way you want to say it, CD, I guess we'll go alphabetized. CD is 60 degrees because the central angle that forms it is also 60 degrees. So this is a diameter, right? It goes through the center from one side of the circle to the other. So what would D to B, what would the measurement of that arc be? Well, if this is a diameter, this is 180 degrees. That's 60. So this is a 120 degree arc. And what's its angle? 120 degree angle, right? So this arc DB is 120 degrees. Now, there's two arcs DB actually. If we look at DB, because there's also the arc right here that would go this way. So this right here all is an arc. So it could go, you know, from the outside. So generally when you talk about that, like on this circle, we would say, what is the measurement of DB that does not go through C? See, because if we go this arc, that one goes through C. That's the difference. That's the one that doesn't go through C would be this one. Okay, so there's two different arcs when you have 2 points in the circle, because it just depends on which way you go around the circle. So from C to B, that arc going through D is 180 degrees. What about the other CB that does not go through D? 180 degrees, right? A circle is 360 degrees. So that's a little bit on measuring arcs. So review that if you need to. I'm going to keep moving here because I don't want to take up your whole day. But we're covering a little bit today about all this. So let's see what we can pull out of this that we're looking at. This image has a circle with two congruent chords. We know what congruent means. Look, they're marked congruent. That means the length of this chord and the length of that chord are identical. So those chords are the same length. So it wants us to draw the central angles associated with the highlighted arcs. We got an arc highlighted here and here. I'm going to go ahead and draw those to the center. There's one. Okay, so there's one angle. Right there. That's one of our central angles. And then going to the other side, the other arc, the central angle that would be correlating to that one is this angle here. Okay, so we have those two angles that are formed with those chords. So how do the measurement of these two central angles, these two angles, what do they appear? Well, they look like they're the same size, don't they? That looks the same. They look the same. So prove that's true. How would we know that's true? Well, let's see. If this chord is the same length, okay, that chord's the same length as this chord. So this arc, the measurement of that arc has to be the same in both of those, whatever it is. Be it 30 degrees, 40 degrees, 37.5 degrees, whatever that is. This arc has to match this arc because it's created with two identical chords. So since central angles equal arc angles measurements, they have to be the same. So since these are the same, that means these arcs are the same, which means these angles would be the same. So we're going to mark those the same. Those are the same angle. What does this tell you about the measures of the highlighted arcs from D to E? Well, they are the same. We know that also. So we could also prove that these were the same without looking at the arcs by saying, well, if these are the same, all the other four parts of those triangles, every one of them is a radius of the circle. They're all a radius of the circle. So it means this one is the same as this one, which is the same as this one, which is the same as this one. So since those are all a radius of the circle, those are all the same length, and these are the same. So by side, 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 those are two similar triangles, which means those two angles have to be the same. Which also means these arcs are the same. It all kind of wraps in together. I like that. We can do a lot with the chords and arcs and central angles and inscribed angles. Going to go one more angle here. All right. A central, here's a circle with a central angle, QAC. All right, you see that? It says use a protractor to find the pro degree. It wants us to do some things with the protractor, mark some points. Tell you what, we're going to do this on the computer. It'll be quicker, easier. We can see the exact same relationship. So let me set that down. Let's switch over here and see what I would say. I've already gone to the computer and created an angle. It's not the same one on there. I just made one. It doesn't really matter. So I have on the screen here an angle that is 110 degrees. You see right there, right there. See the 110 degrees. Now I have a point right here, E, and we can move this point where we want. Put the point. What do you feel like? Yeah, let's put it right there. And if we take this point and we connect it to D and we connect it to C, okay, that's called an inscribed angle. All 3 points of the angle, the vertex and the two ends, are all on the circle. Inscribed. It's in the circle. It's all has a point on the circle. Let's see. What do you think that measurement is going to be? Surely not 110, right? Let's see. 55 degrees. When we connect that, 55 degrees. So the big one from the center is 110, and from the side, when we connect to the same points, still connecting the C and D, is 55. Huh? I must have picked a good spot. It's exactly half, right? So let's try a different spot. How about if I move it way over here? How about this? So now it'll connect to D over there. It'll connect to C up there. What do you think now? It's gotten bigger. Is it 110 now? It's still 55. Wait a minute. Everywhere I move this, the angle stays at 55. Huh. Unless I move it over here, of course, then it's a four-sided quadrilateral, which means they should add up to 360, right? Because over here, oh, see, it's a four-sided shape. Oh, that then adds up to 345. That's kind of weird. Oh, because we have these little angles in there that we have to count too. But so this angle and this angle add up to 345, and you pick up some others. But inscribed angles compared to the central angle is half. Now maybe that's just a coincidence. So let's just leave that one there and change this angle, okay, and see what happens. Oh, look, it's always half. Make this a little bitty angle. Make it 24.48. The inscribed angle is 12.24. It's half. So it doesn't matter how big we make it. Let's make this in a really big angle. That's 300. It's over 300, right? 300.28, 150.14. This is a really big angle now, and still it's half of that one. So that's a special relationship between central angles and inscribed angles. So if you have 2 points on the side of a circle and you make that central angle out there, if you know what that equals, how many degrees that angle equals, you can make another point on the circle and connect it to those same points and know it's exactly half. Or we can go the other way. If we have an inscribed angle that goes from all 3 points of the circle and we know what it measures, we could go from the center to those same 2 points and double it because we know it's twice the size. So, kind of a cool thing. I do want to skip over and show you. I made a special case over here. Let's see. If we look at this one, 180 degrees. I did a diameter. All right, I did a diameter on this, 180 degrees. That's the central angle, and here's the inscribed angle. Right, 90 degrees. That's what we would expect from what we just saw, 90 degrees. But that tells us something even cooler, because if we move this around, that stays 90 degrees. That's a 90-degree angle. Anywhere, of course, that'll work over here, 270, because it's counting the green side of the angle, but the inside of it is 90. So that's what was going on with our other one. It was looking at the other side of the angle. We didn't have the 360. We had the opposite side of the 360. But 90-degree angle. So now we know if you have a diameter and you have another point and you connect it to the ends of that diameter, it's always a 90-degree angle, always. Because that diameter is always 180 degrees. It goes right through the center, it goes from one side to the other, it's half the circle, it's 180 degrees. So any point that you use on the circle and connect to those two ends of the diameter that's on the circle. So all 3 points of your triangle on the circle, always going to be a 90-degree triangle. That's a pretty cool thing about circles. All right, pretty cool thing. All right, let me leave that. Let's get back to this. That's what this was wanting to see. We wanted to see that any point on there was going to be half the angle of that. So let me get off that. I got one more page for you. One more page, and then I'm going to turn you loose with some problems to kind of practice these things. Looking at chords, arcs, central angles, inscribed angles, and just get a little practice with that so you can kind of get used to that. All right, here is a circle that has chords. CD right there. CB across there, EB, ED, and EB. So those are all chords. So these are short chords, but these are long chords. They still go from one side to another. You know, I mean, technically a diameter is a chord. It's just a line segment, straight line going from one side to the other. So chords can be short or long. Just have to be straight lines, and the ends are on the circle. So the highlighted arc from point C to point E, right here, C to E, is 100 degrees. So this is a 100-degree arc right there, which would have been measured from the center point, which we don't have here. So that would be the same as the angle from the center point, right? And D to B, this other one that's highlighted, is a 140-degree arc. And we're supposed to prove that this triangle and this triangle, the two triangles that are formed inside, are similar. They're not congruent, obviously. One's bigger than the other one, but similar. How can we prove those are similar? Well, I'll tell you what. Let me do a little highlighting and see if something kind of shows up here that we didn't notice at first. If I take from this C and E, and I say if I went to point D, right there, that's an inscribed angle, right? All 3 points are on the circle. It's inscribed on there. And I don't have the central angle to compare it to, but I know that the central angle equals 100 because it's the same as the arc. We already saw that. The central angle and the arc have the same degree. So since that's 100 degrees, and this is an inscribed angle, this has to be what? 50-degree angle. It has to be half. Has to be half. It's half of what the central angle is. It's half of what the arc is, because the arc is the same as the central angle. Wonderful. Okay, well that tells me something. So let me look at it this way now. If I go from the other point B and I take it all the way over to C also, that's another inscribed angle. It goes from C to B to E. See, it's all 3 points on the circle. That's an inscribed angle. So this angle here would have to be half of whatever the central angle is, which would be the same as what the arc is. So it would also have to be 50 degrees. Hey, we're getting somewhere. Both of those are 50-degree angles. Well, that's good. That gets us started. But we have this other one that we know about that we can use that too. So if we went the other direction and said, okay, let's look at these 2 points and then the inscribed angle that would connect those, right? So that angle there would be an inscribed angle that would connect both of those, correct? So if we went here to here, the central angle would be the same as what the arc measures. That's 140. So the inscribed angle should be half. This is a 70-degree angle in that corner of the triangle, 70 degrees. So by the same token, if we were to, I'm going to use the yellow and highlight the other way. This one's already yellow. So this angle now that goes to B and D, I just Just like I was doing on the computer screen, I take this E and I just move it over here. It becomes C. I can move it around anywhere, and it did not change what the inscribed angle was. So that one's 70. This is 140, so that's still half of it. That's also 70. Huh. So by angle, those are similar. And actually, if you remember, those are vertical angles. So we know those are the same as each other. So we do have angle, but we only need two angles in a triangle for them to be similar, because that third one has to be the same if two of them are, right? So there's a lot we can get out of circles. When we put angles and when we inscribe them in there where all the points are on the circle, or where we're using the center point, we're going to play around with this over the next few lessons. But I want you, in your assignment today, you'll look at some of this and you'll identify chords and diameters and some of this. So if you need to review this, come on back, take a look at it. It's pretty cool stuff. Circles are pretty fascinating. But that'll be it for today. We will see you next time. Do work you can be proud of.